Unit 5, Topic 3, Euler Paths and Euler Circuits. The main idea, the graph basics have been covered, but one question remains. Is it possible to cover all the edges of an entire graph? If you want to watch a YouTube video, there's one here. We'll go through the definitions and some examples, and that video is available as well. A path that uses every edge is called an Euler path. This type of path does not need to go back to the starting vertex. Remember, that's a circuit, so we're just looking at a path. Figure below is an example. So here we can go A to C to D to A to B to D to E to B. So see, we are able to cover all the edges. All right, let's go down. An Euler circuit is a circuit that uses every edge with no repeats. Since this is a circuit, it must start and end at the same vertex. So here's an example. It's kind of like the house with a little V in the middle. So here, if we were to start at A, we go A to E to C to A. Notice that vertex is getting repeated, not the edges. Then we go to B to C to F to E to D back to A. So we started at A and we ended at A. And we didn't repeat any edges. We only repeated a vertex here or there. Now we have something called Euler's Theorem. If we look back at our graph, let's ask the question, does this graph have an Euler circuit? A few tries will say you can't create an Euler circuit. That's just if you were looking at like a graph and trying to find it yourself. You might not be able to see it right away or find it right off the bat. We're primarily interested in whether an Euler path or circuit exists. Not necessarily that you can figure it out, but that whether or not it exists. Why do we care if an Euler circuit exists? Think back to our housing development lawn inspector from the beginning of the unit. The lawn inspector is interested in walking as little as possible. The ideal situation would be a circuit that covers every street with no repeats. That would be an Euler circuit. Euler solved the question of whether or not an Euler path or circuit will exist. So think about it this way. This actually, the concept of this is used in order to make things as efficient as possible, right? You don't want to repeat paths, and this could be applicable in all sorts of things. So here's the theorem, Euler's path and circuit theorem. A graph will contain an Euler path if it contains at most two vertices of odd degree. So remember, the degree of a vertex is how many edges are coming off of it. So here we have, here we have a vertex with 1. That's a degree of 1. Here we have one with 2, 3, 4 edges. That's an even degree. Here we have one with 0. That's also even. Here we have one with, let's say, 3. That's an odd degree, right? So these two would have an odd degree. So what we're saying is if you have a graph with at most 2 vertices with an odd degree, an Euler path does exist. A graph will contain an Euler circuit if all vertices have an even degree. So that's saying that all of them have to be even. You can't have any with an odd degree. So let's look at this example. So here we have the degree of A is 4. The degree of B is 2. So far they're all even. The degree of D is 3. So that 3 right there tells us that we do not have an Euler circuit because we have at least one vertex with an odd degree. C here has 4, so it's a degree of 4, and E has a degree of 1. That means, going back up here, that a graph will contain an Euler path if it contains at most 2 vertices of odd degree. Well, here we only have 2 vertices, D and E, with odd degrees, so we would say that yes, this has an Euler path. All right, let's go take a look at the homework a few homework examples. All right, here we've got question, is the path A, B, C, D, E, F, D in the graph below a valid Euler circuit or path? Well, without even looking too much into it, we already know right here this vertex A has only 1 degree. It's got 1 edge coming off of it. So right there, we've already ruled out an Euler circuit because it, as we just discussed, they can only have an even degrees on all the vertices. So let's see if we have at most 2. So B has 2, C has 2, D has 3. So right now we have 2 vertices with an odd degree. E has 2 and F also has 2, so that means there is an Euler path. So let's see. It is a valid Euler circuit? No. It is a path but not an Euler path. Well, we are saying there is an Euler path. It is not an Euler circuit or path because it uses an edge more than once. Not true. And it is not a valid Euler circuit because it does not end where it began. Well, that is true. So let's see. Perfect. Your hard work is paying off. So even though it being an Euler path wasn't an option, we were able to find the right one, that it's not an Euler circuit. So here's another example. Is the path ACDABD in the graph below a valid Euler circuit or path? Well, let's take a quick look. I'm going to tell you right now that we do not have an Euler circuit because look, vertex A has 1, 2, 3 edges coming off of it. So we already know that's not the case. So now we're going to see if there's an Euler path. So let's start. We have A to C to D to, D to A to B to D. Well, so far that looks like a path. Let's just double check. See, these both have an even degree, and these two have an odd degree. So we have at most two that have an odd degree, and we're able to use every edge. So I would say it is an Euler path. All right, so our options are it is not an Euler circuit or path because it uses an edge more than once. Well, we didn't use an edge more than once, but it's not an Euler circuit because we don't end. See how we started at A and we ended at D. So that's right there off the bat. It is not a valid Euler circuit because it does not end where it began. Well, we know that's true. So let's just double check everything else. It said it is a valid Euler circuit. We know that's not true. And it is a path, but not an Euler path. Well, that's not true either because we decided that it is an Euler path. All right, perfect. Your hard work is paying off. All right, so next one, if a connected graph has no even vertices and 18 odd vertices, can the graph have an Euler circuit? No, because it says you can't have any odd vertices to have an Euler circuit. So the answer would be no. Great work. The graph below represents bus routes between several different cities. Could a person take each bus route once and only once and end in the same city where they started? Well, when I hear end in the same city where they started, we're talking about a circuit. And since it's saying each bus route once and only once, what it's saying is this an Euler circuit? So this is kind of an applicable, this is definitely an applicable, a good application of an Euler circuit. So what it's asking, we got to go back to that theorem, that it is an Euler circuit if all vertices have even degrees, right? So in this case, A has an even degree, G has an even degree, B has degree of 4, that's even, F is even, E is even, D is even, and C is even. And it looks like that would be, yes, an Euler circuit. Great work. All right, let's take a look at one more. Is the path AD, well, we'll go through the path after we finish reading. In the graph below, a valid Euler circuit or path. So we're looking at AD, C, D, E, B, F, A. Well, first of all, we start and end at the same place. They all have an even, because I'm looking around, we have 2, 2, 2, 2, 4, 2. So they all have an even, and none of the edges were repeated. So it does look like it is a valid Euler circuit. So we're going to go with that last option, submit. All right, so that is the overview and some examples of Unit 5, Topic 3. So if you have any questions about that or anything else, let me know.